So I want to talk about rehabilitating side-by-side voided box girder bridges with ultra-high performance concrete. And so let me start off by what gets me out of bed in the morning. And I'm a civil engineer by training, and I get very excited about anything that I can do to improve the quality of life for society. And our quality of life is based on basically providing clean water, sanitation, and movement, housing, and goods and people. And what better material to do this than concrete? And the best concrete to use is ultra-high performance concrete. And I'm not the least bit biased. So that's really what gets me out of bed in the morning, and that's what excites me about this material. And I believe it is a really good material that builds sustainable infrastructure for the future. And I'm giving a presentation on Wednesday about the sustainability of UHPC. So if you're interested in that, you can check on the sustainability presentations, and I'll talk a little bit about embodied carbon and how it reduces the carbon in the life cycle of a bridge using UHPC compared to other conventional constructions. But that's the topic for another discussion on Wednesday. Today I'm going to talk about side-by-side box girders, what they are, the failure mechanisms, properties, some key properties of UHPC, and then how can we use it for rehabilitation. So I think most people probably know what a side-by-side voided box girder bridge looks like, but I put a picture in here to show what it looks like in reality. So these box girders here are designed to have a slab across the top. So basically you have voided boxes that are sitting side by side, and because they're narrow, when you have the wheel load from a truck, it would concentrate primarily on one box. So in order to get load distribution to adjacent boxes, we have to somehow interconnect the boxes. So the way we do that is with a shear key. So that shear key is at the top, but if you put a Girder shear key in there, it won't necessarily hold the bridge together. So one of the techniques is to put lateral post tensioning. So in this case here, you see a lateral post tensioning, compressing the grout in the connections and holding the boxes together to provide the load distribution. So over time, what happens is you have relaxation, you have creep, and you lose that compression in the girders. So what happens is now the grout and the joints start to work more, and you get differential movement between those side-by-side box girders. There are other ways to do that load distribution, like a very thick concrete slab on top. Those are some of the different techniques, but in this case here, one of the more common ways is lateral post tension. So what happens is, over time, with the relaxation of that strand, you get differential movement between those connections, so the shear keys start to work, and you get reflective cracking in the deck above. It was a concrete deck. In some cases you have a membrane and asphalt on top, but you get reflective cracking in the asphalt, and you'll notice that the boxes are not, the post tension is no longer functioning, the boxes are starting to move differentially. You get reflective cracking, which allows moisture to get in, salt chlorides, causes the boxes to not work as a composite system, and you start to have degradation in the deck. So, this is where the UHPC comes in terms of repair. So, I already explained to everybody what UHPC is. It's basically a cement composite material with enhanced strength, durability, and ductility compared to high-performance concrete. So here's a direct tension coupon. This is a dog bone specimen pulling in direct tension to calculate the tensile capacity of the material. So we have to make a number of samples. We test them, and we characterize the tensile properties of the material. So here you see on the right is a curve from that direct tensile test. So you have the linear elastic zone, you have a first crack, you have strain hardening, and you get a series of micro cracks which continue to load the specimen until you get to the ultimate capacity. You get a localization of the crack, and you start to get strain softening behavior. So UHPC typical compressive strengths are in the range of 17 to 30,000 psi compared to normal concrete, which is like 3 to 6,000 psi. Direct tensile strength of normal concrete is in a range of 150 to 450 psi, whereas UHPC is in the range of more like 900 to 2,500 psi direct tensile strength. The elastic modulus, 3.6 times 10 to the 6, 44, 4.4 times 10 to the 6 psi versus 6 to 7.2 for the UHPC. Now I put permeability here, and I use it as a proxy for durability. One of the big important properties of UHPC is its low permeability. It has a very low permeability. What you can see here is 2 order of magnitudes better than normal concrete. It's 1 order of magnitude better than high performance concrete. Most of the durability properties of UHPC are an order of magnitude better than high performance concrete. It has a very low permeability. It's that low permeability that gives it its durability properties. You have porosity, but the pores are discontinuous. So vapors, water do not migrate and move within the matrix. So if it can't get in, it can't cause the matrix to deteriorate. So this is really what I call a proxy for durability, showing the permeability relative to regular concrete. So it has very, very good resistance to freezing and thawing, chloride, abrasion, all of the properties that cause bridges to fail prematurely. It has very good durability with all those properties. Okay, so I want to talk about applications of this technology. So I'm going to talk about 2 solutions for repairing side-by-side box girders. And the first one is a project in Miami, Florida. So this was a single-span side-by-side box girder bridge that had reflective cracking, and the Florida Department of Transportation decided to try and do a UHPC rehabilitation on this. And this particular one, they wanted to remove the growth, and they wanted to put UHPC back into the shear keys. So first thing they did was mill off the asphalt, and of course when they're milling off the asphalt, the contractor got a little bit carried away, and he milled off part of the concrete on top of the boxes. And you can't see it very well here, but there's some stirrups exposed in the top of the boxes. So we actually ended up doing a little bit of a UHPC overlay to repair that in the project. That was not part of the original intent, but we did it anyway, and it did the repair. So once they milled off the asphalt and exposed the concrete, they brought in a hydro demo machine. They laid down some steel plates on both sides of the shear keys, and they did a hydro demo to remove all the growth and some of the concrete on both sides. So what they did was they actually made an 8-inch by 8-inch shear key. And then they actually drilled down into the boxes and put a U-bar, and epoxied the U-bar. So here you see one of the longitudinal keys with the U-bars. You can see the U-bars epoxied in, and that's approximately 8 by 8. They left a 1-foot section at either end of the boxes, which is over the abutment, where you don't have any differential shear anyway. They left a 1-foot section there because these are post-tension. They're pre-stressed. They're pre-stressed strands in the top of the boxes. But since these are simply supported, these strands are more for transportation rather than in service. But to ensure they didn't lose the pre-stress in the top strands, they left a 1-foot section at either end to make sure the strands were anchored at either end, because they did expose the strand a little bit when they started to do the hydro demo. So you can see they removed all the growth and widened up the connections. They put in the U-bars and were ready to supply and install UHPC. So it was a very small job. Each of those longitudinal joints took a little bit under a half a cubic yard of material. So we've just brought in a small iron mixer, which is a sort of a high shear mixer. And we batched up the material in that mixer. And of course, you have to do certain tests on the material, so we do a flow test in every batch, do a temperature. And Florida DOT also wants you to do bycad initial set, and they also like to do loss of workability. So that means that we cast the material, we do a flow test, we take a 5-gallon pail, we fill it up with UHPC, take a sample, we do a flow test, and it's a standard brass cone, cement flow test with a cone condition spread. And so we do that every 10 minutes to determine when we lose workability down to a 6-inch spread. And that's when they decide that that's workability that's too low to replace, so that's the cutoff. So in this particular test, we ran, this material was coming out of the mixer this day at 95 degrees Fahrenheit. And we did a lot of workability, and we went at 1 hour and stopped the test. So we were still having a reasonable workability up to 1 hour with the material. So once the material is batched, we put it into a wheelbarrow and you stuff it into the connection. So what they're doing here is they're putting, in this case here, we normally specify form grade plywood, but they didn't have form grade plywood, so they used a vinyl strip with burlap in the back, laid that down and then put the plywood on top of it. So you can see here the formwork in place. I'm putting the formwork in place on the left, on top of the connection. This bridge was pretty flat, so you almost could eliminate the formwork here because there's no flow. But a lot of bridges are on slope, skew, across, whatever. So in that case, because it's a self-leveling material, we'll start from the bottom, work our way to the top, and put the forms on as well. Okay, this is another side-by-side box girder bridge. This is actually two bridges. This is on Interstate 88 between Albany and Binghamton, New York. It's about halfway between in Richmondville. And so the contractor had a contract for 10 miles of rehabilitation, 2 lanes northbound, 2 lanes southbound. So he shut down the entirely 2 lanes for 10 miles in one summer, the entire 10-mile section. They rehabilitated all the pavement and 5 bridges. One bridge, they did UHPC overlay, the other 4 they did PPC. So this was the UHPC overlay bridge in year 1. So they milled off 1 3/4 inches of the concrete on top. And on the left, you see there's some burlap where they're wetting it, and you'll see some longitudinal formwork that we've been laying at the time for casting an overlay. So they actually, after they did the milling, they milled off the 1 3/4 inches, then they run a hybrid demo machine over the top to remove any deteriorated concrete. So the 1 3/4 removal gives it the grade, and then the hybrid demo comes through and removes any deteriorated concrete that's not taken out by the milling. One of the nice things about the hybrid demo, it only takes out bad concrete and leaves good concrete. So you end up with a very rough texture, which you'll see on the right, which we call a moonscape. And so it's very rough, but it does not create any micro fissures with that removal process. You end up with a very sound surface and a very good surface to bond with. And then we put water on to saturate the surface dry, and we're ready to place the UHPC onto the deck. So here, in this particular project, we use two 2.65 cubic yard mixers. So these mixers are set up at the far end of the bridge. So we're batching one, unloading the other. There's a bulk bag on the trailer, 1 bulk bag in the mixer, water, 4 bags of fibers, and admixture, and mix, and you're ready to dump into the buggy. So there's 2 ways we can consolidate this mix. This is what we call a fix-of-profit mix. So it's a mix that is fairly it's like a jelly until you put energy in it. Once you put energy in, it liquefies and it becomes self-consolidated. So we use either a vibrating grease screed or a special UHPC paving machine. Either one of these can place it. It depends on the size of the bridge, the volume you need to lay down, and a number of other factors. So on the left, you see a vibrating grease screed running down on the 2 rails, placing the material in front of the screed. And on the right, you see a buggy dumping in front of the paving machine. So here you see, on the far left, you'll see the 2 buggies dumping the UHPC in front of the screed. The screed is moving forward, and immediately behind, they're putting on the white pigmented curing compound because UHPC has no bleed water, so you must cover it immediately. So as soon as you place it, you spray on the curing compound and keep going. So that's what it looks like coming out of the buggy, and once the energy stops, the material becomes semi-solid or stable until you put the energy back in and move it again. Okay, so in this particular project, we did a number of passes longitudinally. So we had an edge form, and we had to pour up against the previous layer. So I wanted to show here on the right, after we stripped the form, the material was between 8 and 10,000 psi compressive strength. So we cast it the day before, we came in the next morning, and it was between 8 and 10,000. We stripped off the edge form and went along the edge. Basically, it's a wire brush on an electric drill, just a small hand drill, and the lead were put along the edge of the slab of the drill. and cleaned up some of the taste and exposed the fiber. So in that 8 to 10,000 psi, you can use just a hand drill with a wire brush, and it gives you a very nice roughened texture, and it exposes the fibers so when you cast up against it, you get a very good bond with the adjacent lane. So once we put the curing compound on, we wait until the material has its initial set, and then we'll put polyethylene on top to provide additional curing. And we'll leave that on until we get to about 10,000 psi. We'll take off the membrane, and so this was the bridge we did a couple years ago, and they did not do anything to the surface after it hit 10,000. They took off the polyethylene and they left it. And so I happened to be back by about 38 days after we cast that, and I wanted to have a look at it and see what it looked like before they did any grinding and gluing. And I'll show you some pictures of that in a minute, but I include this slide because I arrived there just after it had stopped raining and the sun came out, and it's the perfect time because if there's any cracks in that deck, they'll migrate. The water will migrate into the crack, and the sun comes up and dries the surface with the white pigmented curing compound. You can see the cracks very, very easily. So I walked that deck and I wanted to see if there was any treatment crackers, and there was 0 cracking in the bridge at 38 days. So then I did the grinding and grooving, and I came back again after 90 days of service after the grinding and grooving, and I walked it again and couldn't see any cracks. And then the following year we did the adjacent bridge on the other side, because there's been one side 1 year, the other side the other year. And while I was back a year later working on the other bridge, I managed to go back and walk the original bridge. And I was there several days, so I managed to be there on the day right after it rained again, so I could walk the bridge and see any cracks that may show up. And there was no visual cracks except one location. We cast the overlay from end of approach lab to end of approach lab. This was simply supposed bridge with boxes that, and over the top of the abutment on each end of the boxes. It was originally an expansion joint, but they removed that. And when we did the overlay, we cast the bridge over top, and we did not put any expansion joint. So as the boxes deflect, you're going to have some negative bending or tension over the piers. And so I expected to see some pretty major cracking possibly, because we only put 1 3/4 inches on top of that deck. But in actual fact, we couldn't see any cracking to the naked eye. But after the rain, when the moisture migrated, the sun came over and dried the surface, you could see some hairline cracks over the top of the box on each end of the bridge. That was the only evidence of cracking. Let's see my presentation.